Yeah, you can begin.
Okay, so good evening to all of you. Welcome to the day two and fourth session of Curry Leaf Days 2023, which is being delivered by Dr. Sankara Raju on BEXT, proximity points, and proximal normal structure. This talk is being organized by Curry Leaf, a math club of MTTS alumni in collaboration with MTTS Trust. The invited speaker, Dr. Raju, is currently an associate professor in the Department of Mathematics at IIT Ropar. Doctor Raju carried out postdoctoral studies at ISI Bangalore and earned his PhD in mathematics from IIT Madras. Dr. Raju's areas of research interest include matrix analysis, geometric aspects of functional analysis, approximation theory, and applications. We are happy to have Dr. Raju with us today. A warm welcome to him. Now, I would like to invite P. Tapan Patro to give general instructions for Zoom audience and YouTube viewers. So, Tapan, over to you.
Hello, here's some basic instruction to the Zoom audience and YouTube viewers. In that case, if you have any question, raise your hand. Then one of the host or co-host will call out your name. Then you can ask your question to the speaker. In case of YouTube viewers, you have any question, feel free to post your question in chat box. We will convey your question to the speaker. Okay.
Okay, thank you, Tapan. Now, I would like to hand over the session to our esteemed speaker, Dr. Raju. So, sir, over to you.
Yeah, good evening all, and thank you Jyoti and all for giving me opportunity. So without delay, I will start. As instructed by the organizers, I would like to go my talk in a very elementary way. You know? So if any speaker has any doubts, you can ask me. Just you can raise your hand in the Zoom so that I will stop for a while and we can discuss. Just let me share first. I hope my screen is visible to all.
Yes.
Yeah, my today I would like to discuss very elementary results on fixed point theory connected with some geometric aspects. Most of them are in literature survey. I will at the end I will quote one or two results which were carried out from my group. But time sake, I will prefer everything on the literature survey with basics. So let me start with a metric space. In my complete my talk, X denotes either metric space unless otherwise if I specify any other space. So and in this metric space, D is the metric distance function, and I will denote cap big ABs are subsets of X. So for any set A, diameter, we will define diameter of the set. Suppose let us say this is some A set. Diameter we will denote as the largest distance between any two elements of the set A. We will denote it by diameter of A. Diameter of A is exactly supremum of distance from any two elements taken from the set A. And if this is A and this is B, this gap, the minimum distance between one element from A and another from element from B, we will denote it by D of AB or distance of AB, or we will call it as gap between AB. On the other hand, this largest distance, the supremum of distances, one coming from A, another coming from B, we call it as diameter, relative diameter of AB. Relative diameter of AB is supremum distance between xy, where x is coming from A and y is coming from B. These are the basic notations we use in our talk. Using this, first we will recall one of the very fundamental and interesting results in fixed point theorem, which is by Banach, that states that if we have any function from x to x and f satisfies the following condition: distance between any images is less or equals to distance between alpha times distance between pre-images, where alpha is some constant in 0, 1. If there exists a alpha that satisfies this condition, for all xy in x, and such a f we call it as contraction. For such contraction, Banach in 1922 proved that there exists some x star in x such that f of x star is same with f of x. F of x star is same with x star. While if we consider x is a complete normally metric space, if we have a complete metric space and f is a contraction on x, then we will have an x star satisfying this property, and such a point which satisfies that property we call it as fixed point of f. Such a x star we call it as fixed point of the function f. And more than this, we can observe from the proof that if we start any initial point x0 in x, and if we look at the sequence x0, x1, x2, like xn sequence, where xn is f of xn minus 1. That means that x1 is f of x0, x2 is f of x1, x3 is f of x2, and all. In that case, the sequence xn converges to the fixed point. And the conclusion of the Banach fixed point theorem is, if we have a complete metric space and if we have a function f which is a contraction, then we can have a unique fixed point x star for the function f. And not only that, these are called Picard iterates. These Picard iterates will converges to the fixed point. And as an extension of this, we can as an extension of this, we can think of functions of this type. Suppose what will happen if I have a function from x to x that satisfies first property, that satisfies, if it is satisfies distance from f of x and f of y is lesser or equals to distance from x to y. That means that such kind of maps are called non-expansive maps. In our earlier case, our alpha is 1. So non-expansive mappings, for non-expansive mapping, can we get any results on fixed point? That means, is there any guarantee for the existence of fixed point for non-expansive maps? The second type of mappings are contractive mappings. This says that suppose if we have a function f from x to x that satisfies distance from f, the image distance of the images is strictly less than distance of pre-images. This we call it as contractive maps. For contractive maps, is there any guarantee for the existence of fixed point? Third map what we consider in this talk is ellipsis maps. That defines as distance between images is less or equals to k times distance between pre-images for some k is bigger equals to 1. For such maps, we will call this as ellipses in mappings. So in our talk, we will mostly concentrate on these three type of mappings. Existence of fixed points or not for such kind of mappings. As we discussed earlier, in 1922, Banach established Banach contraction theorem, which says that if we have a complete metric space and a contraction mapping on the complete metric space, we will have a unique fixed point with the property. The more than that, the Picard's iterates for given any initial point x naught, the Picard iterates will converge to the unique fixed point. This impacts this results impacts much in numeric analysis. Anyway, we are not going to do much applications here. Just I would like to discuss only geometry of this, how geometry is involved for such kind of maps. So after 1922, it's maybe around 1962, Eldestein proves that if we have a x nonlinear space and A is a compact convex subset, subset of x, then any contractive map on A possesses a fixed point. Of course, this is unique, and not only unique, the Picard iterates will converge to the unique fixed points. Later in 1965, two major results appeared for non-expansive mapping. One is by Browder, which says that if X is a Hilbert space and A is compact convex, compact and convex, then every non-expansive map possesses a fixed point, and the geometry connection between fixed points as well as non-expansive mappings is given by 1965 by Kirk by introducing a geometrical notion. The notion is the following. Yes, let us take any x. For time being, we are fixing this is a nonlinear space and A some subset of x. So how the geometric notion is connected is, suppose this is A. Look at any point x and look at the diameter, the largest distance from this to the boundary. That means that look at take any x, fix any x in A, and look at the diameter of this set singles and set A, singles and set X and A, which is defined as supremum of distance between X and small a, where small a is coming from A. If our set A satisfies the property that there exists one element X in A such that the diameter of this, simply we will write this as diameter of XA. The diameter of XA is strictly less than diameter of A. That means that this is, suppose our diameter of A is, let us say, this much, and we can able to find X such that this diameter is strictly less than this diameter, then we say that X is a non-diametral point for A. For A. Such X is called as non-diametral point of A. The quick result says that if our A possesses at least one non-diametral point, then a non-expansive mappings will have a fixed point. For example, I will complete the statement. Let us say, let A be a closed convex subset of a nonlinear space. Of course, we need weakly compactness also, some type of compactness. Suppose A has a non-diametral point. Then we say that give me a second, not only non-diametral point, sorry, I will define one more geometrical structure. So if we have any X, if for this A, suppose if we have X which satisfies this property, that means that which has a, which, suppose X is a non-diametral point. Let me, this X we call it as a non-diametral point. Further, for every subset C of A has a non-diametral point, then we say that A has normal structure. Normal structure means given any subset of a nonlinear space, given any subset like this, if we take any subset of that every subset will have one non-diametral point. This is X1. For one set we will have one non-diametral point, another set we will have another non-diametral point. Every subset we will have, there is some signal issues. Is my audio visible? Am I audible? I hope yes.
Yes.
Yes, sir, you are audible.
Okay. So if suppose we have a subset A of a nonlinear space, we say that this A has a normal structure if every subset C of A has a non-diameter point. For this means for every subset C, we will have a X such that diameter from X to C will be strictly less than diameter of C. If such a if A satisfies that one, we say that A is having A is having A satisfies or A has the normal structure. In 1965, Crick proved that if we have a subset, let A be a subset of a nonlinear space which is weakly closed and compact, having normal structure, and if we have a function from A to A which satisfies our if we satisfies non-expansive property, that means that if we have a non-expansive map on A, then A will have at least one fixed point. Then there exists at least one x star in A such that f of x star is same with f of x. That means f of x star is a fixed point of F. Here we can see that this normal structure is in general not holds uh, for um, for any subset of A, but we can see that in some spaces, let us say in uniformly convex Banach spaces, it will satisfy. Let us define what is uniformly convex Banach space. For this, first we will define strictly convex Banach space. Suppose a nonlinear space, let us say nonlinear space, X is a nonlinear space, let us say L2, R2. Suppose we have an R2. Let us look at our unit ball. What is unit ball? I am looking at the boundary of the circle radius 1 with center 0. We are looking at set of all elements in R2 such that norm of x. Of course, I am taking 2 norm. 2 norm means this is so if you look at this unit ball, and if we take any 2 points on the boundary, let us look at its midpoint. Its midpoint will be always inside the circle. If any nonlinear space satisfies this property, we call it that space as strictly convex space. We say that X is strictly convex. We say that a space X is strictly convex if we take any X and Y which are not same in the unit ball. So we will define this is unit ball. This is boundary as Bx. Bx is set of all elements of X such that whose norm exactly equals to 1. If xy belongs to, then if we take this one, then we will have the midpoint x plus y by 2 norm will be strictly less than 1. If a space satisfying this property, then we say that this is strictly convex. Now let us see, there are other spaces. Let us see, for example, R2 with 3 norm, R2 with norm 3. What is meaning of R2 with norm 3 is our space is R2. That means that our elements are order pairs. But we are taking norm of any element as modulus of x cube, x1 cube, modulus of x1, x2 cube, whole power 1 by 3. With respect to this norm, let us see what will be the unit ball. What is our unit ball? In this case, our Bx is set of all x in R2 such that norm of x with respect to this 3 norm is exactly 1. This is no more like a circle. We can get like exactly some oval type of thing. It is not a circle. It is some oval kind of thing we will get. Even though if we take any two elements, here if we look at earlier thing in L2, if we take any 2 points, suppose let us take 2 points here with respect to 2 norm, 2 points here, another 2 points, let us say 1 point here and 1 point here. The midpoint is with the proper, suppose earlier I have taken two points xy on the boundary such a way that the distances is same with this distance. I have taken two pair of points in R2 such a way that here the distance xy distance is same with xy distance. In R2 with respect to 2 norm, this the distance between midpoint of these two to boundary is same with distance between midpoint to boundary here in R2. That is not true in general in R3. Suppose if I take distance here, this gap, if I take any 2 points with the same distance, whatever may be the distance here, if I take this distance, this midpoint to this distance may not be same in general. So if that is the same, in that case, we will call it as uniformly convex space. I will write formally definition, then I will explain the geometry. Uniform convex Banach space is, suppose we have a let X is a nonlinear space. X is a nonlinear space. Choose any xy in the boundary of the unit ball. That means that whose norms are 1 with the property that anywhere with the property that these two distances are greater than epsilon. So what so roughly I will write, if I take xy as well as uv in bx as well as some pq in bx with the property that norm of x minus b, the distance between x minus y is same with distance between u minus v is same with distance between p minus q. In this case, what we need, suppose in this case, what we need is the midpoint the distance from boundary to the midpoint should be greater than some delta, and this delta is independent of choosing of pairs. If suppose this is some epsilon, I should get a delta such that whatever the pair I choose, wherever I can choose, that the distance is equals to epsilon or bigger than epsilon, then this midpoint, that means that here the midpoint should be greater than, the gap should be delta. Here also the gap should be delta. If I choose here 2 points with the same distance of this x to y, here also the midpoint delta. So irrespective of my pair, wherever I choose on the boundary, and my pair is satisfying that the pair distance is epsilon, then the midpoint is at least delta away from the boundary. If I get that uniform delta, we call that space as uniformly convex Banach space. For example, there are examples. Suppose let us see, I have a space where my unit ball may like this. In this case, if I take xy here, the distance is this much. But if I take xy here, the distance is less. Such kind of thing cannot happen for uniformly convex Banach space. So classically, how we define is, a nonlinear space is said to be uniformly convex Banach space if for given epsilon greater than 0, there exists a delta greater than 0, such that whenever xy in the unit boundary of the unit ball with the property that norm of x minus y will be greater equals to epsilon, then we will have the midpoint of xy is at least delta units away from the boundary. If such a thing can happen, we say that our space is uniformly convex Banach space. And it has been proved that if we take any closed convex subset of closed convex bounded subset of uniformly convex Banach space, it will have normal structure. So we will recall this one later. Later, still now we are looking for fixed points of a map which is from x to x. Suppose x is in metric space. If we have a function from x to x, we are looking at the conditions on either f or on x such that we can have a point satisfying this property. In general, there is no guarantee of existence of this kind of point. On the other hand, there are functions that will be like this. Suppose x is a map from x to x, where k to x, where k is a subset of x. In that case, it is not easy to verify fixed points because these are not self maps. Because we can this kind of maps, we can think of elements of k. Suppose this is our x and this is our k. Elements of k can be mapped to outside of k. In this case, this is not easy to it is not like valid for thinking of fixed points always. In this case, Key-Fan proved that in this case, we may not expect fixed point, but we can expect a point such a way that nearer to k. Suppose we can expect x, which is this is x star, such a way that t of x star is the f of x star is this one, such a way that the distance is minimum. Equivalently, what we are looking for is, look at fixed point is fixed point is, we can think fixed point on the other hand as an optimization problem for this function. If we can able to find one x star where this is 0, then we are to, that is fixed point. Now what key fan produced is, in this case, in such kind of cases, instead of looking for fixed points, we can look for points x star such a way that distance from distance from x star to f of x star minimum in some sense. What is this minimum is? This is distance from f of x star to a. That means that, look at x star, this is the best approximation of a. What is meaning of best approximation of a? The minimal element which is nearer to f of x star will be x star itself. Later in 2005, Professor Veeramani and all extended such kind of maps in these directions. Let us take a function from A to B, where A and B are two subsets of a nonlinear space. And since we are taking arbitrary subsets of x, it is not reasonable to expect fixed point. If it has a fixed point, this intersection should be non-empty, but we have not taken this kind of condition. In this case, they explored the existence of a point x star in A, for which x star and f of x star is very nearby. That is equivalently saying that they explored existence of a point x star in A such that distance between x star and f of x star is this distance is same with distance between AB. What is geometrically meaning that, suppose we have, this is A and this is B, we can able to find x star here and f of x star here. This is the smallest distance. Distance from x star and f of x star is same with distance between AB, and such type of points are called best proximity point. Best proximity point. And they proved by using the proximal normal structure, which is an extension of normal structure. What is proximal normal structure is, proximal normal structure is, we can recall normal structure here. Normal structure is, given any subset A of a nonlinear space, if I take, it will have one non-diametral point. Not it. Every subset of A will have a non-diametral point. The distance between x star, the diameter between x star and A will be strictly less than diameter of A. So proximal normal structure, how we can extend from this is, suppose let us take any two subsets. Fix one point x star and look at the diameter of x star to B. Similarly, look at fix one point y star and look at the diameter of y star to B. These two, or maximum of these two, should be less than diameter from A to B. So equivalently saying that there exists one point X star in A and Y star in B, another point Y star in B, such that diameter of X star to B is strictly less than proximal diameter of AB, which is the maximum distance from one element from A, another element from B, as well as the same condition with Y star. The diameter from Y star to B, Y star to A, this diameter, this Y star to A, the maximum the diameter from Y star to A also should be less than diameter of AB. If such a X star Y star exists, then we say that these are proximal non-diametral points of AB. Proximal normal structure defines as a pair AB is said to be proximal normal structure. Every subpair of AB will have proximal diametral points. That means that for any subpair H of AB, what is meaning of subpair is this H is subset of A, K is subset of B. For any of these, there exist proximal non-diametral points. Proximal non-diametral points. That means there exists X star such that X star, there exists X star in K such that distance diameter of X star to K is strictly less than proximal diameter of HK. There exists a Y star in K such that the diameter from Y star to H is strictly less than the proximal diameter of HK. In this case, they have proved that, of course, using convexity, they have proved that if we have any function A union B to A union B satisfying cyclic nature, that means F maps A elements to B and B elements to A. In this case, if we have A, B are convex weakly compact subsets of a nonlinear space satisfying proximal proximal normal structure, then it will have best proximity points. That means that in this case there exists a X star Y star satisfying distance from X star to F of X star is same with distance between AB, gap between AB, which is same with distance from Y star to F of Y star. That means that if F satisfies all the conditions, then we will get X star here, F of X star here. Similarly, Y star here, F of Y star here. Now, we have extended for this into uniformly normal structure case. What is uniform proximal normal structure is uniform proximal normal structure, which says that look at a pair of subsets. In this pair, look at this collection. Suppose H and K, which is subset of AB. That means that H is subset of A, K is subset of B. In that case, look at non-diametral, the distance between, we have in this case, for proximal normal structure, we have the property that diameter of xk is strictly less than diameter of hk, where x belongs to A, as well as diameter of yh is less than diameter of hk. Equivalently saying that diameter of xk by diameter of hk is strictly less than 1, as well as diameter of yh by diameter of hk is strictly less than 1. Normal structure says that this holds for every subpair of AB. And what we extended is not only this holds, furthermore, we can have the supremum is less than 1. Supremum of, let us take xk by delta of hk, where take the supremum taken over all collection of pairs hks which are subsets of ab's. This is less than 1, as well as this one also. So if this supremum less than 1, then we say that the pair will have uniform proximal normal structure. And in this case, we have proved that we have established the following result, which states that if f is any function which is from A union B to A union B, which is cyclic, f of A is subset of B and f of B is subset of A, and the pair AB has proximal uniform normal structure. How we define this one? That our pair will satisfy this one. In that case, of course, A and B are bounded convex subsets of a nonlinear space. Then there exists a x star, y star in A cross B. That means x is in A, y is in B, such that the distance between x star and f of x star is same with the gap between AB, which is same with distance between y star and f of y star. Sorry. The result is interesting because here the proximal uniform normal structure will replaces weak compactness. So in this case, we don't need to assume compactness either weak sense or in another sense, because this uniformness will taking care of some type of compactness, and also this will exist. This guarantees the existence of points like this. Suppose, let us say, first of all, suppose if we have A and B, at least we can for existence of this point, we should have at least there exists one point x in A such that distance between xy is equals to distance between AB for some y. If there is no x satisfying this one, then there is no we cannot expect this kind of results. So this uniform proximal normal structure guarantees the existence of such point. That is the first important first essential property to get rid of compactness. Another one is to existence of this one. Of course, there are a couple of open problems. For example, till now we are unable to succeed this proximal uniform normal structure. Does a uniformly convex Banach space, if we take AB as a closed convex sets, then can we have proximal uniform normal structure? This is very very geometrically, like we are unable to proceed due to several issues. For example, the pairs. For example, let us see in R2 with respect to infinity. Now, if we look at these lines, suppose this is 0 0 1 0, this is 1 1, this is 0 1, these lines, any distance between any 2 points from one side, one point here, this side to one point this side will be same with distance between these two sides. That means that here what I here distance between a, this is our a, suppose let us say this is our a, this is our b, distance between a b is 1, as well as if I take any x in a, y in b, distance between x and y is also 1. So geometrically establishing even in uniformly convex Banach space, every closed convex bounded pair having proximal uniform normal structure is a non-trivial problem. So we are on the way, but we could not able to succeed on that. So uh, if some yeah, yes, I will stop with this. Hello.
Yes.
Yeah.
Jyoti?
Hello.
Yes. Yes. Yes.
Yes, am I audible to you?
Yes. Yes. Yes.
Yeah. Okay, so thank you, sir, for such insightful talk. Now it's time for Q&A session. So participants, feel free to ask questions.
Can you give some references for this?
Yeah. Yeah. References are I will. Shall I tell or shall I write?
Maybe you can write. You
Yes.
can share the screen and yeah.
Yeah. Fixed point theorems results I am taking from book from Kirk, fixed point metric fixed point theory. And proximal normal structure. In this book we will have normal structure as well as Banach contraction and extension results, and further all fixed point results we can get. For proximal normal structure I am taking I am for I like Professor P Veeramani and he eldered. It is in 2005 studio math paper. And uniform normal structure from myself and Big Digger. In 2022 Annals of Function Analysis paper.
Okay, thank you.
Yeah.
Okay, thank you, sir.
Yes.
Now, thank you for the amazing class. Now we are going to take a group photo. I would like to request you all to turn on your camera for the group photo.
And sir, you can stop sharing.
Yeah, that's fine.
Yeah, thank you. Okay, others can also switch on their videos. Okay, so with the countdown of 1 to 3, we will take the photograph. So 1, 2, 3. Okay, so thanks to all of you.
Yeah, thank you, Jyoti. Actually,
Yeah, thank you, sir.